8.1. The distribution of the sample mean. A probability distribution for all possible values of the statistic computed from a sample size of n is called a sampling distribution. When we take a sampling distribution of the sample mean, there are 3 steps we need to follow. First, we obtain a simple random sample of size n. Then we compute the sample mean. So that gives us one sample mean. Then we're going to repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. So let's take a look at an example. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. Approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equals 5 from this population. The data on the following slide represent the sample means for the 200 simple random samples of size n equals 5. For example, the first sample of n equals 5 had the following data. So when they weighed the first sample of 5 pennies, these are the different weights that they had. And so when you find the sample mean for that, you get 2.479 for that particular sample. So now on the next slide, we're going to look at the sample means, the mean of 200 different samples. So here are all the different sample means from this 200 samples that were taken. The mean of that set of 200 sample means is 2.46, which you'll notice is the same as the population that we talked about in the original problem. The standard deviation, however, is 0.0086, which is smaller than the standard deviation of the population. So now let's take a look at the histogram of those sample means. And you can see that it's pretty normally distributed, and the mean is at 2.46. So now let's take a look at the impact that a sample size has on the sampling variability. So we're going to approximate the sampling distribution of the sample mean by obtaining 200 simple random samples, but this time we're going to look at samples of size 20. So again, here was our histogram for when our sample size was 5. And now look what happens when our sample size is 20. When we increase the size of the sample, our distribution has less variability. So the distribution is much closer together. And so you can see that now our standard deviation is 0.0045, which is much smaller. It's about half almost of the sample standard deviation when n equaled 5. So the larger the samples, the less variability you have. Now suppose that a simple random sample of size n is drawn from a large population with mean mu and standard deviation sigma. The sampling distribution of x bar will have a mean that is equal to the population mean, and then the standard deviation is going to be the population standard deviation divided by the square root of the sample size. The standard deviation of the sampling distribution of x bar is called the standard error of the mean, and that's denoted with sigma sub x bar. So when you take the population standard deviation and you divide by the square root of the sample size, that is the standard error of the mean. So now let's describe the distribution. Again, we're looking at the weights of the pennies, and so you have the mean and the standard deviation there. What is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams? All right, so we know that our mean is going to be the same as the population mean, and that should actually say mu sub x bar, not mu sub x. But it's the same as the population mean. But then our standard error of the mean, or the standard deviation, is 0.02, because that was the standard deviation of the population, divided by the square root of 10, because that's the size of the sample in this new problem. So we get 0.0063. So then we're going to find our z-score, because we have our x value, which was 2.465, that was given to us in the problem. Remember that we're wanting to find a sample mean of at least 2.465, and then we subtract our mean and divide by the standard deviation, and that gives us the z-score. So we get 0.79, and then we use that to look at the table, and here's a diagram of where that z-score lies in the distribution, and see that it's to the right of the mu, or the mean, and we want at least 2.465, so we're going to shade to the right, which means when we find the probability of that z-score, we need to make sure we subtract it from 1 in order to get the probability. And so we get the probability is about 21.48%. So the probability that in a simple random sample of 10 pennies minted after 1982, the probability that we obtain a sample mean of at least 2.465 grams is about 21.5%. Now let's take a look at something called the central limit theorem. So here we have the theoretical probability of rolling a die and it landing on a 1, a 2, a 3, a 4, a 5, or a 6. So notice that all the probabilities are exactly the same. They're all 1/6. Now let's take a look. And you can see that the mean is 3.5 and your standard deviation is 1.708. Now let's take a look at the distribution when you take 200 samples of size 4 and you calculate the mean. And now let's take a look and see what happens when our sample size increases to 10. And then when it increases to 30. So notice what's going on here in this problem. You're seeing that the larger the sample size, the more normal the distribution becomes. So let's use this theorem. Suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2 minutes. So the first part of the problem says, if a random sample of n equals 35 oil changes is selected, describe the sampling distribution of the sample mean. So we know that x bar, or the sample mean, is approximately normally distributed with a mean equal to 11.4 minutes and a standard deviation of 0.5409 minutes. If a random sample of n equals 35 oil changes is selected, what is the probability the mean oil change time is less than 11 minutes? So now we're going to use that mean and the standard deviation and our x value of 11 to find the z-score. And when we do that, we get negative 0.74, so we look that up in the table, and we find that our probability is 0.23. So there's a 23% chance that the oil change time is going to be less than 11 minutes. And that is the distribution of the sample mean.